is chapter 1. So in the beginning, you are going to take a look at, let me just make that bigger. Okay, a single degree of freedom system. All right, so if you look at your schedule or your notes, you are dealing with single degree of freedom system with M and K. So the first part, normally we talk about free vibrations, means there is no input to the system. Okay, so and then we talk about, this is still single degree of freedom system. And we divided normally for undamped and also damped. So after we talk about undamped, so we also take a look at a damped system. So both is still single degree of freedom system for free vibration. So definition of free vibration is when you do not have any input to the system. All right. So this is what we call undamped, because you do not have any damper. So this is what we call damped, because you have your C there. So that's the main difference. So we cover that in chapter 2 basically. So this is chapter 2. All right. Okay, then we go ahead, move to chapter 3. So chapter 3, maybe I can change. So the next chapter is chapter 3. You're gonna learn about harmonically excited. Okay, what it means by harmonically excited system. You are still dealing with single degree of freedom system, yeah, but it's harmonically excited. Sometimes harmonically excited is also called as forced, because you have input to the system. So if I want to draw that, so we also gonna talk about the undamped. Okay. So normally you have input to the system, and your input is normally a sine or a cosine function. So that's why it is called harmonically excited, because sine or cosine function is an example of harmonically excited input. Because you know the input is the input is harmonics, yeah. So you're gonna take a look at two cases as well. For this one, you're gonna take a look at damped and also undamped. And of course, you're gonna see later on there are different type of cases as well. So you are still dealing a sine or a cosine function. So X is your output to this system. So similarly, you're going to take a look at undamped and damped condition. All right. And of course, in section chapter 3, you are going to look at 3 different types of system. Later on, you're going to have a fixed base. There are 3 systems. Base motion, okay, and also rotating unbalance. So All right. Then we move on. Okay. Chapter 4, we didn't touch in details. We talk about energy, energy methods, but we go ahead and go on to chapter 5, basically, if you look at your textbook. So all these are all about a single degree of freedom system. All right. So after you've done all this, you're gonna have your midterm. So this is where you're gonna have your midterm. So you can see that's why in most semesters, a lot of students get 100% because midterm is so easy. So the test, 20% of your grades is so easy peasy because you only deal with single degree of freedom system. That's it. So make sure you understand the topics, yeah? So after midterm, you're going to take a look at 2 degree of freedom system, which is chapter 5. So in 2 degree of freedom system, we talk about free and force as well. So now instead of you have 1 mass, you're going to have 2 masses because it's 2 degree of freedom system. Okay, it can be damped, it can be undamped. Okay, it can be you can also have forces. Force input, it can be sine, it can be cosine. Okay, of course, the first part of chapter 5 is actually free vibration, free 2 degree of freedom system, but in chapter 6, you learn how to solve when you have input to the system, you have to solve what we call using the modal analysis. So modal analysis is basically methods that you use to solve a 2 degree of freedom system with force, what we call force vibration, to solve a force vibration of a 2 degree of freedom system. So because you cannot solve it directly, so you want to use modal analysis to solve the force vibration of a 2 degree of freedom system. In chapter 5 is just free vibration, yeah. So chapter 6 is on the force vibration of 2 degree of freedom system. Then you go, once you're done with 2 degree of freedom system, then you go to chapter 8. Chapter 8 is on continuous system. Maybe I spell it wrong. Continuous, continuous. N-U-O-U-S, continuous system. Okay, so continuous system refers to you cannot see like a mass like this. Continuous system can be your beam problem. Okay, can be your bar problem or shaft problem. So these are types of continuous system where you cannot actually have a model to write on the masses discretely. Yeah, your X is basically your position on the bar or on the beam. Okay, where your points are continuous. You cannot differentiate between M1, M2, M3, and so on. It can be infinite. Yeah. So that's what you deal with continuous system. And finally, after you've done with, you have to take a look at a single degree of freedom system, a 2 degree of freedom system. You are going to use, okay, you are going to use knowledge from single degree of freedom system, chapter 2, chapter 3, and chapter 5. You are using this knowledge back to conclude how do you solve for your vibration control. In chapter 9, so it's kind of neat where you actually get to solve vibration problems using the knowledge from chapter 1, chapter 2, 3, and 5. So in vibration control, if you look at a single degree of freedom system, you are actually dealing with designing an isolator. And when you have absorber, you are dealing with, so this is actually your isolator. And when you have your absorber, you are using the 2 degree of freedom model. All right. So this part here is the isolator. This part here is the absorber. All right. Any questions so far? Easy peasy, isn't it? So maybe this can be machine. So you're going to take a look at real problem. So what is important basically in this course, you need to try to look at real problems. How do you model it? And at the end, we recap with how do you actually control it. Any question, class? So that's the overview of the course. Easy peasy. Okay, any question? No?
So far, okay.
So far, so good. Very good. So maybe we go real quick on the first part. Okay, notice that I keep on mentioning chapter 2 and so on, yeah? Chapter 1, what is chapter 1? Chapter 1 is basically the fundamental vibrations. We talk about the basic concepts and basically we want you to understand some of the terms, okay? You may want to read that on your own in details as well, like degree of freedom, discrete, continuous system. I think I've explained that a little bit. Discrete system is something like your single degree, 2 degree, yeah, versus continuous system. How do you see every single thing in this world in terms of stiffness, okay? And see how if it's parallel, if it's series, you need to know how to determine equivalent mass, okay, equivalent spring and damping constants of any vibrating systems. Okay, and understand the definition of free force. Okay, I've explained to you just now. Free means there is no input to the system. Force means there is input to the system. Okay, then take a look at the damp undamp. I also explained that with my figure just now, yeah. Okay, we're going to take a look at that in a while as well. All right, in practice, okay, what happens in practice? Okay, you know that maybe there are good parts of how we use the mechanical vibrations in our everyday life. You know, for example, from condition monitoring, if you have vibrations, then you know that can be an indicator of the condition of the machine, yeah, for example. So that's why it's beneficial to keep the mechanical vibrations there, because we want to know what happens to the system. Or if you want to design a sieve, okay, or mixers or tools, so you need the movement or the vibrations that can do the job, okay, as well as all these important things. It is bad when it comes to maybe your transportation. You don't want vibration in your transportation, isn't it? Because there's going to be noise, there's going to be discomfort, failures, okay, motion sickness, and so on. Okay, if you notice there is a video actually in your Brighton, you can check that out, or maybe you can go to YouTube and search on the Tacoma Narrows Bridge. Okay, it's actually twisting. Okay, so this is an example of a phenomenon, you know, how this thing happened. And it basically shows that you can see that there's a twisting motion of the Tacoma Bridge. And you can see that when the twisting motion was at maximum, the elevation of the sidewalk was 28 feet or 8.5 meters. So that's really, really high. So that can cause problem. And finally, it actually failed. So you can see that the bridge fails basically. So these are some of the vibration problems that we can relate with our everyday life that is important for us to solve. Okay. So this is another example. We have shearing shaft, okay, due to the high torsional vibrations. So if you deal with a lot of machineries in industries, so this is where the mechanical engineers work, isn't it? In any industries, you're gonna deal with a lot of issues in terms of if you don't control the vibrations. And a lot of time it causes by having the speed at the vicinity of the torsional natural frequency in this case. In other words, what we call the resonance. So in this class, we also talk a lot about resonance because that causes high amplitude of vibrations. Quite similarly to the Tacoma Bridge, it is found that the wind speed actually hit the bridge that causes some frequency, and that matches with the frequency of the wind hitting the bridge. That causes some resonance there. All right, examples of vibrating system. So we have masses attached to the spring, okay, as shown in A, flexible rods. So we also have pendulum problem. You're going to take a look at all this. How do you actually do the modeling? Yeah. Okay. Some of the important concepts in the theory, so it can be categorized into the following: the element parts of vibrating system, degree of freedom, discrete, and continuous. So there is a definition to all those things. And you need to know when things are vibrating, then there is energy related to it. Okay, so a system must be able to store energy into different forms and allow energy to be transferred from one to the other. So that's why you can also get your EOM based on the energy method. Yeah. So in particular, there must be a transfer of energy from potential to kinetic and vice versa. So that's what happens when you have vibration. So potential energy is due to, so there are two things. So normally when we say gravity and elasticity of the system. So if you look at any system, when you use energy method, so normally it relates with the gravity, because if you know the equation is, if you have change of height, for example, the formula is mgh. Elasticity of the system can comes from your stiffness, K. All right, so normally the energy equation is half K x squared if it's linear system. Okay, so that's where your potential energy comes. And for kinetic energy, okay, so if we talk about kinetic energy, it's basically due to the motion of the mass. So normally if you look at any mass, you have your mx double dot, isn't it? So that will be your acceleration, and the energy equation is half mv square. So half mx dot square. So those are the equation. So when you differentiate that, you get mx. Sorry, maybe this will be a bit confusing because I want to write in terms of energy. So if you remember your physics, it's half mv square, so that's why half mx dot square. Okay. So in fundamentals of vibration, it is important for you to know how to get this equivalent mass, equivalent stiffness, and equivalent damping. And you also need to know how to convert from linear system to torsional system. So for example, for a spring, okay, if you have a spring like this, okay, you can actually write the force of a linear spring in terms of kx. Okay, if it's torsional, it's ktx. So the kt is different, has different units than k. So that's why we give different variables there. So when you deal with a torsional, you can see that the displacement, okay, for linear is x, displacement for torsional is theta. So this is what we call rotational displacement. Okay, theta. So K is linear stiffness, KT is torsional stiffness. All right. Okay, so for example, if you want to write potential energy, so for linear, we write it as half kx squared. Okay. For torsional or rotational, there is another term, rotational. We can write it as half kt theta square. All right, instead of x, then you have to write it in terms of theta. And instead of k, you have it in terms of kt. Okay. So there are various configurations, and maybe you need to make sure you're familiar with the terms when we talk about longitudinal motion, which is the vibration in the direction of the length, transverse vibration, which is perpendicular to the length, and torsional means you're rotating. So that's the difference, yeah, between longitudinal, transverse, and also torsional. Okay, there are other equations, okay, when we talk about equivalent stiffness. So there are other equations that you can use. For example, if you have a mass hanging like this stiffness, equivalent stiffness, okay, can be defined as EA over L, or because it experienced longitudinal vibration. So it depends on the arrangement. How do you get this equation? You can take a look at in front of the textbook. You have all these equivalent stiffness and equivalent mass equation. So this is how you model every day in our life in terms of equivalent stiffness. Okay, how do you find the values? Yeah, so it's based on the properties or the arrangement of your structures, basically. I think you should come across this in engineering measurement, where you use stiffness as part of measurement equipment. All right, this is an example of stiffness associated with torsional. So when you have a shaft, a rotating shaft, or motor with a shaft, then you may have this torsional vibration, and you can actually calculate the stiffness of the shaft or the rod here, yeah, based on this equation. So depending on the structures itself. So this is another example, stiffness associated with a helical spring. Spring-like structures would have different equations. This is also quite common when you have a cantilever, what we call the transverse vibration of the tip of a beam when you have a mass. So you can calculate the equivalent stiffness as 3EI over L cubed. So these are the different types of stiffness. So when you analyze any system, you have to look at the structures. How do you compute the equivalent stiffness? And the arrangement can be in two ways, a combination of parallel and series. So if it's parallel, you take the summation, but if it's in series, you have to take the inverse of the summation. So you may want to memorize that part. The next part is talking about mass or inertial elements. And as we said, this inertial element or mass, okay, if it's rotational, we change it into I or J. I think most of our notes we use J, yeah. This is old notes, we use I. So it doesn't matter as long as you understand. So in terms of, can you tell me what kind of energy relates to mass, class? I just told you just now. Any of you? What kind of energy? Yeah, is it kinetic or potential?
Kinetic.
Very good. So you do have kinetic energy when you have mass. And if it's linear, what is the equation, class? Anybody?
You mean F equals to mx, madam?
The equation for kinetic energy for linear. You have two types of motion, linear and rotational. Yeah, if it's kinetic energy, what is the equation? Have
mv square.
mv square. Very good. So mv square means you have to write in terms of x, so x dot square. What about rotational, class? Have. So instead of m, what do you have? Instead of m, what do you have?
K, madam.
J. Okay, so m is the linear mass. The rotational mass, we call it J. Very good. Okay, what about x? Instead of x dot, what do you have?
Theta.
Theta. Very good. So rotational displacement is theta. So the equation is J theta dot square. Okay, so this is also, you're going to see this later on, but just to make sure that you're familiar with all these basic things. The M, what are the equations related to M? What are the equations related to K? What are equations related to C? Okay, so these are the three main elements in vibration. All right, so there's an explanation there. So there is an example here. How do you actually calculate the equivalent mass of a system? So let's say you have this original system and you want to write the equivalent system. Okay, in other words, from these three masses, M1, M2, M3 at specific location, okay, you want to collapse it into one equivalent mass, which what we call M equivalent. So that's the question, yeah. So in other words, if you have a complicated system, for example, your car, so this is a very real and practical problem. You want to model your car into equivalent stiffness, equivalent mass, and equivalent damping. So that's how it is. Yeah. So that's why you have to understand how to solve this problem. How do you convert with having three masses into collapse it into one mass, and what we call the equivalent system of equivalent mass? Why do you think we want to do this? Anybody? Why do you want to collapse it into one?
To make calculation easier.
To make the calculation easier. Very good. Okay. And also the easiest solution that we have is always what? Single degree of freedom system, isn't it? That's why in a lot of times, either maybe you see the simplest model is having a single degree of freedom system. So that's the intention. So before you know how to solve for SDOF, what is SDOF, class?
Single degree of freedom.
Yes, single degree of freedom system. Okay, so that's why you always want to know, okay, how do I get the equivalent mass, equivalent stiffness, and equivalent damper? Because you want to collapse a complicated system into a single degree of freedom system. So of course, before you want to solve the single degree of freedom system, this is the first step. So that's why this lecture is called fundamental. The first thing that you want to do is, in this case, you want to find M equivalent. So if you look at this, this diagram, basically if I blow it up a little bit, maybe if you want to draw there is kind of like a triangle, isn't it? If I want to draw all across it, it's kind of like a triangle. Can you tell me what is the common displacement that I have for all the three masses, M1, M2, M3? How do you describe the displacement of these three masses? It's kind of like rotating basically, right? What is common of all these three? Is it X or what? Class?
The angle.
The angle data.
Angle, very good, very good. You got it. The angle are all the same, isn't it? And you can also see this kind of problem is basically rotational, but you also have it in terms of X. So you may want to get the relationship between theta and X. So this concept is very important because you're going to use this across the course. So make sure you understand this. Yeah, if you draw a small triangle here, the relationship between x1, x2, and x3 with theta, can anyone give me the relationship? If you, this is kind of like, if you know the formula for an angle, S equals to J theta. Have you heard of that formula before? Have you heard of that? J is jejari, or I don't know, it can be anything. Radius, basically. Have you heard of that formula? S is equals to J theta.
Yes, madam.
Yeah. Or your radius, R theta. Okay, tell me then, what is x1 in terms of theta? Using this formula, class?
S.
No, not S. You see this figure here. What is this distance?
L theta.
L1 data.
Ah, very good, very good. So x1 is equals to L1 theta. So we are assuming this is a small displacement, yeah, because this x is kind of like linear, isn't it? But you are actually rotating. So there is an assumption in throughout our course, theta is small. So your linear x is equivalent to curvy x. Okay, so normally all the assumptions, theta is small for all vibration problem. But that's the relationship. Basically, x1 is equals to L1 theta. What about x2? X2
L2
class?
data.
L2 theta. Very good, very good. So this is what we call the trigonometric relationship. Okay, you're going to use this for all bar problem. Later on, you're going to see a lot of these problems throughout the course. So this triangle or this shape you will see appear. This is what we call, you can see the title, translational masses connected by a rigid bar, or it's not just masses, any springs maybe, if we connect a spring at certain position. So this kind of triangle that we are looking at has a trigonometric relationship. So when you have these three relationships, you can equate theta, isn't it? So what is theta? So theta, let me just write that here. So basically you can write everything in terms of theta is equals to x1 over L1, same, x2 equals over L2, and x3 over L3. All right. So if you look at this, then you see that this equivalent system, you want to express everything in terms of x dot equivalent, which is the assumption this x dot equivalent is equals to x dot 1. So you want to actually express all the x dot 2 and x dot 3 in terms of x dot equivalent or x dot 1 is the same, isn't it? Right? So how do you do that? So you express, so this is also equals to x dot 1. Yeah. So take note, it's the same, x dot 1 or x1. If you're talking about dot, you just put a dot here. So that's the difference. Are you with me? It's the same, yeah? Although it's displacement or vibration. So if you want to express in terms of velocity, then you just put dot to the x and you have the same relationship. Okay. So how do you express x dot 2? So that's why you get x dot 2 is equals to L2 x dot 1 over L1. Okay, are you with me? Let me write that again. Make sure you ask me the question. Can you see? If I rearrange this term, if I rearrange this term, okay, what do I get? Sorry, this one too. X dot 2 equals to what? Plus x dot 2 equals to L2 over L1 x dot 1. Okay, are you with me? Are you with me?
Yes, madam.
Okay,
Yes.
very good. So that's how you get the trigonometric relationship. So do the same thing. Do the same thing for x dot 3 over L3 equals to x dot 1 L1. So you rearrange. So you get x dot 3 is equals to L3 x dot 1 or x dot equivalent over L1. Okay, so that's how you get this. Okay, once you get that, okay, shall we move on? Okay, clear? Once you get the trigonometric relationship, okay, you can actually write it using the kinetic energy. So that's why I was emphasizing on the equation, yeah, using kinetic energy to get the equivalent mass. So you use the kinetic energy equation. So how do you do that? So you can see, you write here. So this is the equivalent system. Basically, you should put it on the left-hand side because you want to find What do you want to find? Your M equivalent. That is what you want to find. So you're supposed to put in the left-hand side of the equation. Equals to, then you put, alamak, nak be battery dah. Then you put the original system. So this is the equivalent system equals to this is the original system. Are you with me? Do you understand? You have to write, because remember you have three masses, right? M1, M2, and M3. So you want to write the kinetic energy for all the three systems. Okay. Any questions so far? Let me just put my battery on. Class, any question?
No.
Thank you, thank you. Okay. All right, so once you do that, what you need to do, you just substitute, because what do you want to get rid, class? You want to find M equivalent. So what do you want to strike through? What do you want to cancel if you want to get M equivalent? This one can cancel out, right?
Half.
Yeah, and your X equivalent is equals to X dot 1, isn't it? Okay, you want to cancel this out as well, right? So that's why you have the previous equation, you have to write this all in X dot equivalent. This one also have to write everything in X dot equivalent. Okay, this one as well. So then you can cancel out all the X equivalent and left with M equivalent. Okay, where do you get this? So you write back your X dot 2. So these are the equations. You see, you can cancel out the X equivalent. And X dot 3, substitute into that equation. You see you have the X dot equivalent. So you're left with L2 over L1 and L3 over L1. So that's how you get L2 over L1 square and L3 over L1 square. So which is basically from, from this relationship. And you cancel out the X equivalent. Okay, any question from here to here? Is it clear? Okay. Class.
Okay.
Okay, madam. Okay, madam.
Easy peasy. Very good, very good. So there's another problem. So this is also one of the important example where you're going to use this in throughout the course. Okay, this is what we call coupled translational and rotational masses. So this is also very important. So we are using the same concept of the small triangle. If you look at here, you have the kinetic relationship. Okay, how do you relate theta to x? So you can see x is going down. So basically, if I want to draw the relationship between theta and x, I can draw a small triangle here. So this is kind of like your x, because when the mass move x in the x direction, the spring deflect as well as the pulley will actually, the cable on the pulley will also rotate at the same time. And it's being described by, by the small triangle in red. Can anyone tell me what's the equation based on S equals to J theta? What is the equation? X equals to? Look at the variables there.
R theta.
R theta, very good. Okay, so when you have any problem like this, you have to think physically. So I think in mechanical vibration, it's something physical. You have to think of what happens to the movement when you have this kind of system and you relate it with the displacement that you identify. You have to identify the displacement that you want to describe. In this case, they give you x and theta, yeah. So x equals to r theta. So that's why if you want to write in terms of velocity, x equals to r theta dot, that's how you get theta dot equals to x dot over r. So you want to obtain equivalent translational mass. So depending on the question, some questions they want to find the equivalent mass. Some question wants to find maybe equivalent moment, or in this case theta, yeah, equivalent rotational mass. So there, in this case, you have two equations that you want to find in terms of x dot equivalent and in terms of theta dot equivalent. So let us do that. You already have the relationship. Okay, so you have to write, there are two types of mass. One is the m, okay, and one is the j naught. So in energy it's easy. You just identify the element. You have m and j. So write the energy equation for m and j. So it's easy. So you write for m, so that means half m x dot square, and for j, half j naught theta dot square. Okay, it's equivalent to half m equivalent x dot square. So for x dot square, you have the relationship just now. Your x dot equals to theta dot equals to x dot over r. So that's how they get this expression. Okay, so from there you can cancel out the terms and rearrange, and you get the m equivalent. So you can see we are also assuming that your x equivalent, so we already put here, this is the assumption. Your x dot equivalent is equals to x dot, and your theta dot equivalent is equal to the theta dot. So do the same thing for the equivalent rotational mass. Okay, that means you want to solve everything in terms of j equivalent. Just now we want to solve for m equivalent. So you use the kinetic energy as well. This is what you want to find. So you write it in terms of half j equivalent theta dot square equivalent. And your mass, so this is actually x squared and x dot square and theta dot square. You don't have to substitute because you want to cancel out the theta dot, isn't it? So you want to cancel that out. So you have to put everything in terms of theta dot square. Easy. Earlier it should be x dot square, since you have the relationship. Your x dot square is basically equals to theta dot r square. So that's how you get. Then you can cancel out the theta dot square, and the half also you can cancel out. You're left with your j equivalent is mr square plus j naught. Any question? No?
No, madam.
Easy peasy. Okay. So let us take a look at the damping elements. It's the same. You have force for damper is Cx dot. For torsional, Ct theta dot. Okay, tell me the energy for energy equation for the Cx dot. Anybody? For linear, have Cx dot square. Okay. For torsional, what do you think for torsional class? Or rotational? Torsional or rotational? It should be half. Hello?
C theta square.
Yeah, Ct. So to differentiate with that C, theta dot, yeah, don't forget. theta dot square. So those are the energy equation for dampers. Okay. So there are different types of damping elements. We have viscous, Coulomb, and hysteretic. So normally the simplest one, that's why you see a lot of viscous damping that we use as an assumption, because it's proportional, okay? It's linearly proportional to the velocity. It's the easiest damping coefficient, okay? The rest are not linear, yeah? Then you have to know if it's in parallel, very similarly to your stiffness, okay? If it's parallel, you add them up. If it's in series, you take the inverse, the summation of the inverse. Okay, a bit of definition. Degree of freedom is basically the minimum number of independent coordinates required to determine completely the positions of all parts. Okay, so for example, if you have this system, you have unconstrained rigid body with 6 degree of freedom system. So definition of discrete and continuous, we've talked about that. So you have single degree, 2 degree, dots are an example of discrete system. The way you solve it, the equations are different for a discrete system. Chapter 2, 3, 5, all you use second order ordinary differential equation, second ODE. Okay, second order ODE. But for continuous, okay, which is later on you're going to see in chapter 8, this one, chapter 2, 3, and 5. That's why you have that mx double dot, and normally you can just use a normal second order ODE. But for chapter 8, you're going to use partial differential equation, PDE. So this one is ODE, second order ODE. Okay. Classification, we've talked about free and force. Force being having input to the system, damp being having a damper in the system, linear and non-linear, and then you have deterministic and random vibration. Okay, so this is an example of free. You can see it's 0. So this is how you do the modeling. If it's free, there's no input. If it's forced, there's an input. This is undamped because you don't have a C. C is equal to 0. So for damped, C is not equal to 0. For linear, it's saying that the cause force and effect response are proportionally related, because that's why it's called linear. It's where you can actually use principle of superposition. If it's non-linear, you cannot do that. Yeah, there is no cause and effect because it's non-linear. So that is one of the difference basically. Deterministic, if you have a vibration that you can determine the output, for example. So normally a harmonic motion is an example of deterministic because you can actually see the pattern and you know what's coming in and what's coming out. You can predict, okay? So normally for harmonically excited, you use sine function or cosine function, for example. You can model it. But random, okay, you do not know, you cannot determine, yeah, cannot predict. So normally for random vibration, people use statistics or stochastics method to predict the output. So there's one example. We have this composite propeller shaft made of steel and aluminum. So you can see here you have inside is aluminum, and the outside surface is basically the steel. Okay. So, and this is actually torsional force, so it's actually move the steel and the aluminum together. Okay, how many of you says, okay, then you have to determine the equivalent stiffness of the steel and the aluminum of the shaft. How many of you think this is an example of the steel and the aluminum to calculate your equivalent stiffness? Is this series or parallel stiffness? How many of you think this is parallel? Put up your hands. Class. How many think this example is a parallel? Because you have to find K equivalent from K due to aluminum and K due to the steel. And this shaft is experienced torsional. So the movement is to. How many of you think this is a parallel problem? Because the equations, the way you add it up is different. Only what, one of you? What about the rest? Gone for lunch? Okay, 4 of you. Okay, put down your hands. Tambah pula kan? How many of you think it's in series? Put up your hands if you don't think it's in series. How many of you think it's in series? Tak sure pula. Okay, maybe 8, 9, or 12. You think it looks like in series? Okay, thank you. So more people think it's in a series. So it's basically, if you look at, you can download the notes actually. You know the answer. Okay, the way to do it is basically you have to find the equivalent stiffness, okay, based on the torsional stiffness equation. But you have to do it for both material, okay, and you should see that it is actually in parallel. Okay, let me explain. Okay, very good. Good try. I understand. Maybe if you look at from the cross-sectional, yeah, it's as if you see it like this. Okay, steel and aluminum. If you look at this cross-sectional, but basically this is in series. But this shaft experienced torsional. If you think about it physically, okay, if it's experienced torsional means this steel and shaft moves together. I don't know if you can see my video or not. It moves together. So the steel and aluminum, if I want to draw it, is kind of like this. You want to draw it physically, what happens? Yeah. Because it's torsional, yeah, it's torsional. It moves together. So if you think of it physically, the steel and aluminum moves together, kind of like this figure where it is actually parallel. So it's not in series, but it is in parallel. So be careful when you look at any problem. You really have to decide whether it is in series or in parallel. You can have the same shaft in series if maybe you put your force in this direction. It's not torsional. Then maybe the stiffness is in this direction. Then you can have it in series. But this one is torsional. Are you with me, class?
If half aluminium,
susahnya. Half aluminium, half steel.
ah,
Maksudnya? Macam dia
dia
rupa dia.
torsional, tapi dia separuh.
Separuh kat mana? Sini. Sini. Separuh tu kat mana? Oh, you mean like this macam ni is it like this?
Semicircle.
Like this
Yes.
Macam sini steel, sini aluminium Yeah, maybe this can be, you can assume like that. Yeah, that's a good question. I haven't got that question before. Yes, that can possibly be kind of like in series. Very good question. All right, so first thing, you take a look at the structure. I showed you some of the examples in the notes, and take a look at some other examples in front of your textbook. So this is a torsional problem. You can get this torsional stiffness equation for a shaft for that from the textbook, and this is you have inner and outer diameter. You have to calculate for steel. Okay, by using, you can see these different parameters in terms of the shear modulus, G. Okay, the G and the D, the D, outer and inner. So do it for the steel and do it for the aluminum. Since it's in parallel, easy peasy, you just add them up. Okay, any other questions? Actually, I'm done for today. I'm sorry to just like go on non-stop. We just had a brief 5 minutes because I want to finish early.